Hi everyone, this is Hot Topics, topic modeling of a Latin text. I'm Brendan Friesen. We also have Bard Swallow, Martha Durrett, Sam Wiseman, Estelle Bayer, and Adam Klein, and we have been advised by Eric Alexander.
So maybe you saw that New York Times article that came out this past summer about data analysis of Jane Austen. It's a prime example of the growing prominence of a field called the digital humanities. Now, the digital humanities can mean using 3D printing to study archaeological artifacts and inscriptions without getting the actual object. It can mean bringing the past to life by creating a video game-style interactive experience of history, like Carleton's Boston Massacre and Workhouse projects. Last year's Prairie Comp started building a toolkit for that, and their successors will be presenting right after us in the cinema. Digital humanities can also mean natural language processing and data analysis, applied directly to written primary sources, like in the Jane Austen example that made the news. Topic modeling is one of those techniques. What is topic modeling? Well, we're here to tell you about how we turn this into this. First, we'll talk about our motivation and give you an introduction to topic modeling in general. Then we'll talk about the idiosyncrasies of our data and the algorithm we chose. Next, we'll talk about our visualization tool, both our goals and our current implementation. At the end, we'll tell you about some of the limitations of our models and possible next steps for the project. So our data set comes from a project by a group of professors, Rob Hardy, Austin Mason, and Bill North, who have been working on an edition of excerpts from a text by the Venerable Bede for Dickinson College commentaries. The text is called the Historia Ecclesiastica Gentis Anglorum, or the Ecclesiastical History of the English People. It was written around 731 and chronicles the development of the early Anglo-Saxon church and its conflicts about liturgy and rites. It's a major source of our knowledge about Anglo-Saxon history, and its addition to the Dickinson College commentary site is a departure from the site's usual focus on classical texts. When Austin first came to us, he had done some simple frequency analysis on the Bede text. He told us that he felt like he could separate many of the most frequent words into 2 or 3 big topics. His first question for us was whether using topic modeling algorithms on the data would yield some of the same topics he came up with, just from looking at the most common words. But he also said we shouldn't come at the data with too many preconceptions. Our initial models should inform the direction we took and the questions we asked. Choosing an algorithm and how to visualize the data, that would be up to us. We decided we wanted to focus on making a tool rather than just a model, one that gave the user the ability to make adjustments and optimize for texts beyond just the data we were given.
So having made it all the way to this presentation, you may be curious about what this topic modeling thing is. In order to explain what it is and how it works, there are some words and concepts that we should understand. Topic modeling algorithms fall under the umbrella of machine learning. All this really means is that we're trying to search through large amounts of data to find patterns that may not already be obvious to humans. While broadly applicable, topic modeling has especially exciting implications for the digital humanities. And then, in this context, the data put into topic modeling is known as the corpus, a lot of text data. A corpus could be a book, an encyclopedia, a journal, or even a group of social media posts. The important unifying factor is that a corpus can be broken down into many chunks, which we call documents. A document could be something like a magazine article, a chapter of a book, or a blog post. What matters is that it's coherent and combines with other documents to form a corpus. When we run topic modeling on a corpus, the most important output is the topics themselves. A topic is just what it sounds like, a group of words that go together, such as piano, tune, and rhythm, or score, goal, and penalty, or even France, Parliament, and Schengen. Topic modeling puts words in a topic together when they are likely to appear alongside each other in documents. Topic modeling is unsupervised machine learning, which means that it generates patterns by itself with no help from us or from labels in the data. That means that we cannot ask it to do things like, find me every word in the corpus related to penguins, or what role do apples play in this text? We just provide a corpus and a desired number of topics. If a topic is prevalent in the text, it should be picked up by topic modeling regardless. However, just because the program doesn't name topics for us doesn't mean we can't nickname them ourselves once we see them. We might call these topics music topic, sports topic, and European Union topic. As an example to demonstrate, let's consider a corpus that might be a good candidate for topic modeling, Dante's Divine Comedy. It's an epic poem that is divided into 100 cantos, each of which is around 1,000 to 2,000 words long, a great subdivision for this purpose. While feeding it the subdivided corpus, we also need to tell the topic modeling algorithm that we'd like it to identify exactly 10 topics, for instance. After some time in magic, which we'll touch on later, the algorithm produces our 10 topics. Here are some of them. One seems to contain words about heaven. Another one has some geography and some deadly sins. 8 more topics will be produced, grouping semantically related words together. Looking at these topics is a great first step towards understanding what are, in some empirical sense, significant themes in the text. Let's suppose that among these 10 topics, there is one that focuses on God and other holy words. Topic modeling won't just give us a list of those words. Over time, each instance or occurrence of a word is assigned to a topic separately, so words can appear in more than one topic. Likewise, chances are that one word will be placed in the same topic multiple times. Whenever this happens, the word's prevalence, or weight, in the topic increases. In our hypothetical God topic, we can see that the word light is quite prevalent. It comprises over 2% of the words in the topic. We expect that most words will occupy much less space, but this data provides an effective way to observe the relative importance of words during a topic. By observing their prevalence, we are able to identify which words are crucial to the text. While the algorithm doesn't output names for our topics, we can often nickname them based on the words that appear in them many times. Now we have a set of topics and a word distribution associated with each one. Another interesting way we can represent our output is by inspecting the topic makeup of each document. For instance, let's consider Canto 13 of the Divine Comedy. Topic modeling can tell us that around 60% of the words in this canto were placed into what we nicknamed the Inferno topic. Perhaps 20% come from a topic representing Earth and humanity, and another 10% of words had something to do with God. Without even reading this canto, we can already draw inferences about what it's about, what words it uses, and what its role in the overall text may be. For instance, it's probably from the book Inferno. We can consider the rest of the documents, such as document 62 here, as conglomerations or even probability distributions of topics. This information deepens our understanding of our corpus's underlying structure. Thus, the output of topic modeling is threefold. We have a corpus that contains topics, topics that contain weighted words, and documents that contain weighted topics. Topic modeling isn't new, so there are a few algorithms that perform it. Each offers a different approach for generating topics from a text. Describing each of these algorithms would take too much time, but after researching each of them, we decided that the one to implement for our comps was latent Dirichlet allocation, or LDA. Meet me after the presentation if you'd like to discuss the pronunciation. It's been around for a while and has cemented itself as a popular tool in natural language processing libraries like Python's Natural Language Toolkit. It's very flexible, and during our literature review stage, we observed that a significant amount of topic modeling was really just repurposed LDA. So we set our minds to implementing it from scratch for our comps. But before we could even consider how the algorithm works, the data we were given had some challenges that we had to address first.
So our data set wasn't exactly designed for topic modeling. It was designed for this Carleton College commentary site, which is set up with a section for vocabulary notes and definitions. The data set was originally made to catalog every word in the excerpts and their definitions to get them ready for the site. Since it was originally made as a tool to support the bead edition on the site, it contains information only about the chosen excerpts, not the whole text. This means that topic modeling results on this data set will be skewed toward the professor's chosen themes. In choosing the excerpts, which make up about 20% of the whole text, the bead group glossed over a lot of the repetitive historical anecdotes and focused on the rarer, more interesting passages, especially the few focusing on women. While great for an online edition, losing the more homogeneous data will mean that the words most integral to the text, the repetitive ones, will have less weight in the topic model. But we couldn't just scrap the data set and grab the full text online. There was information we absolutely needed in the data that we were given, and that is lemmatized words. So lemmatization takes an inflected word, a word you would find in the text, and turns it into a head word, or a word you would find in the dictionary. So consider the word to be in English. Depending on who is acting, or even when the action happened, the word looks different. But when you go to look it up in the dictionary, there aren't entries for am or was. You want to look under be for to be. And similarly, if you're trying to get the computer to understand that am, is, are, was, and were are all the same word, you want to turn them all into the same string or word so the computer can recognize them and treat them as one unit. And this is called lemmatization. So English inflects verbs and pronouns. Latin inflects verbs and pronouns, but it also inflects nouns. A Latin noun, like rex, will have a different ending based on what it's doing in the sentence. To the king will look different from of the king, which will look different from the king acting as the subject in the sentence. In this case, the inflected form means to the king, because Bede is addressing King Ceolwulf. So if you don't revert all these inflected forms to the head word, you end up with topics that are just collections of different inflections of the same word. Since the dataset was already doing lemmatization in order to look up definitions for words, its data, while smaller than the full text, was still more useful to us than the full unlemmatized text taken from an online version might be.
So having addressed some of those initial challenges that we found in our data set and picking a topic modeling algorithm, we're ready to dive into implementing latent Dirichlet allocation, or LDA, which we sometimes like to call Latin Dirichlet allocation. One of the key principles central to understanding LDA at a conceptual level is the structure of a topic, which Sam touched on earlier. So the colloquial use of topic usually refers to a list of words with some generating theme. So if I say romance, you might start listing love, flowers, chocolate, warmth as a topic. But in a topic modeling sense, we think of a topic as a probability distribution of words and their frequencies, like what we saw with the Dante example, or here, a topic from a Great Gatsby model we generated. So how do we find these topics in a corpus? From a conceptual standpoint, it's a lot like looking around a crowded room and trying to figure out who knows whom. Imagine that this crowd is a corpus, and every person in it is a word. People who know each other are in the same topic. We can guess with a fair amount of confidence that these two people probably know each other. They're standing next to each other, they appear to be talking to each other. Similarly, two words that are in the same document are more likely to be in the same topic. This person, on the other hand, is probably not related to the first two. They're on the other side of the crowd, they're walking away, and similarly, words that are in different documents in different parts of the corpus are less likely to share a topic. But that isn't a universal rule. This person, for example, could be, despite being on the other side of the crowd, could be going to meet our first two. Maybe they have a lunch date set up, but they're currently on opposite sides of the crowd. And similarly, words that are in different documents can still share topics. It would be a little bit strange if you took all of Shakespeare's works as a corpus and the theme of romance only ever occurred in one document or play. So in a crowded room, we have lots of information about people around us. We can read body language, listen to conversations, and we have a number of visual cues to deduce who knows whom. How do we translate this process to words on a corpus, where the only information we actually have is the position of the words? For example, what information do we use to figure out if these two judgments on the first page of the Great Gatsby share our topic? Well, besides the actual words on the page, we can make some inferences using hidden or latent variables, which is where the latent and LDA comes from, like tracking what percentage of every document is comprised of each topic once we've made some topic assignments. And given this information, we can start to look for the information we actually want, which is, given an instance of the word judgments, how likely is it that that instance is going to be in any one of our topics? Here, the two visible judgments have been assigned different topics. And if we extrapolate this to the whole corpus, we might discover that the highest proportion of judgments is in topic 1 with 36%, and topic 2 contains 27% of judgments in the text, and so on and so forth for every topic in the corpus. And then we can use that information to assign topics and obtain a probability distribution like the ones you see here for every topic that we're trying to find in our text. So when it comes to actually implementing this, we decided to use Python, which is a common language in the digital humanities, because it provides robust libraries for text handling, like the natural language toolkit that Sam mentioned earlier, It's high-level syntax, it's easy for less experienced programmers to pick up and get going on quickly, and it allows people to pass around code and freely share and modify it without being bogged down in private variables, which makes it adaptable for varied digital humanities needs. And in order to explain our implementation of LDA, I'm going to walk you through one iteration of the algorithm. That is the process of assigning a new topic to each of the words in the corpus. For this example, we're going to use a very small portion of a corpus with very small documents in it. We're only going to look at in-depth at the first 3 documents, but the corpus likely contains many more. And we can store these documents as ordered lists of words inside an ordered list of documents. Thus, when we want to access any given word, we can access it easily through careful indexing of documents and words. So given this structure, we then adapt it to something that looks like this, where we removed all the sort of semantically insignificant words that we wouldn't want in our eventual model because they don't contribute much meaning, and which we'll go into more depth later. And then we assign an arbitrary topic to each word in the corpus just to begin. And we can track these topic assignments in a couple of key ways. The first is a structure that stores the words assigned to each topic and how many instances of that word are in each topic. So for example, topic 1 there contains the word wristwatch 1 time. Topic 3 contains bedlam 1 time. And then, pardon me, the second structure that we use is parallels the word and document storage that I mentioned earlier, except instead of containing individual words, it contains topic assignments. So having created this framework, we can begin the process of adjusting our topic assignments from the sort of arbitrarily chosen ones we started with. We do so 1 word at a time, and when assigning a new topic, we always assume that every other word has been correctly assigned a topic in order to make our inferences. So starting at the beginning of the corpus, we remove 1 word at a time from the topic structure. Here we remove the assignment of time to topic 1 in order to determine a new non-arbitrary assignment for it. And we also update our topic tracking accordingly, so the word time now has 0 occurrences in topic 1. And we can begin the process of calculating what probability the word time occurs in each topic, starting with topic 1. The first step is to determine what % of a given topic is comprised of the word in question. Since there are no occurrences of time in topic 1 after removing it, this is a 0% occurrence here. And then we can determine how frequently the topic in question occurs in the document that contains the word we removed. So we can see that topic 1 occurs 1 time in the document that contains 5 words. So there's a 20% occurrence of topic 1 in document 1. And using the previous 2 calculations, we want to determine and track the probability that time is assigned to any given topic. We can visualize the underlying principle with a 2-dimensional figure whose width is proportional to how much of the topic is comprised of the word time. And in this case, there is no width, since time does not occur in topic 1. And the height of the figure represents the % of the document that the word is assigned to topic 1. Where am I? Sorry, folks, I'm having some technical difficulties. There we go. And we're presenting this probability as an area, but this figure would have no area since it doesn't have width right now. And we want topics to be able to take on new words, even if that word didn't originally exist there. So we use these things called hyperparameters, which are a special variable that basically gives us a little bit of wiggle room and creates area even if there wasn't necessarily going to be word area there. And then we can come up with this shape that represents the likelihood that time will be assigned to topic 1. And looking at the same word in the corpus, we can then make the same calculations that we did for topic 1, but focusing on topic 2 instead. Here, because the word time appears in topic 2 already, we don't obtain a 0% occurrence. And we also calculate what proportion of document 1 is made up of topic 2. And having done this, we can generate a similar figure to the one we made for topic 1 with respect to the word time. We can see at a glance that time is much more likely to be assigned to topic 2 than it is to topic 1. And finally, we calculate the probability that time is in topic 3. Now we want to use these stored probabilities to probabilistically assign time to a new topic. Well, algorithmically, this is done through stored percentages and NumPy's random library. It's easier to visualize this process with the graphs we've created. So once we've created them, we combine them into one figure that we can consider sort of a target space for our magic perfectly fair dart. This dart will always hit something in the target space when thrown, and it is equally likely to hit any individual coordinate position in the target space. In this case, we throw our dart, and we get topic 2 as the new assignment for this instance of the word time. So we reassign time, replace the word in the corpus with the new assignment, and we're going to update the topic location accordingly, incrementing the occurrences of time in topic 2 so that it is now occurs twice in topic 2 instead of once, and then also updating our topic tracking structure so that the first word in the first corpus is assigned to topic 2. Then we move on to the next word in the corpus, tragic. We deassign its topic, and we start this whole process over again by removing it from the corpus and determining what the new topic assignment should be with our information. And once we've completed these steps for every word in the corpus, we have completed one iteration of the LDA algorithm. A single topic model, like the ones we are going to be showing you at the end with our visualizations, may take dozens, hundreds, or even thousands of iterations to generate, depending on the number of parameters that we use.
So running our implementation of LDA comes down to one call in the command line. We pass our parameters through a configuration file, one of those parameters, obviously the most important one, is your source file, which contains the text you want to analyze. And so you can do that in just a plain text file or with a CSV. And if you're putting a CSV in, that means that you have one column for the words, and you also have a column for which documents those words came from. So you have that chunking data already there. Whereas if you submit a text file to it, then you will have to use other parameters to split that text into documents. The user also has to give the number of iterations of LDA that they want to be run. So these bars represent the prevalence of one topic across a corpus. And the darkness of the bar is basically how many words are being assigned to that topic in that location of the bar. So as you can imagine, the more uniform the bar, the less data clustering has occurred. So the topic is being sort of assigned evenly throughout. The more color separation, the more the data has clustered, the more certain topics are being expressed in certain locations. As you can imagine, we want there to be more separation. We want the data to cluster nicely. And you can see that over more iterations, the data does cluster. And so the most significant changes occur near the beginning, but we have found that you need to run at least around 50 iterations before you get the data to settle and to cluster nicely. Another parameter is the number of topics. LDA doesn't really know anything about what the appropriate number of topics in the corpus is. And so this is a number that you really have to find by just trying different things when you run LDA. We imagine that longer corpora will be able to talk about more themes over their length, and therefore you try to ballpark a number with, more topics. And so that column on the far right is how many topics we found to be the sweet spot that gave our most significant topic results for that corpus. And so there are types of words that LDA doesn't really play well with. And so we're going to have to remove those before running LDA. The first group is the semantically insignificant words like the, and, is, or not. And those can't really be tied reasonably to any theme or topic in a corpus, and so we want to remove those. Another group is the infrequent words. If you have a corpus with hundreds of thousands of words and you have a word like incoronation that only shows up twice in the corpus, then there's no way it can ever be a significant part of any topic. So we want to make sure to remove those as well. There are also probably names in the corpus, and we want to remove those because running LDA with names included reveals that LDA has a tendency to form topics around characters rather than around the themes of the text, and so it's a distracting factor. Another group of stop words is the frequent words. And the problem with having words that occur too frequently in your corpus is that they're likely to be prominent in many topics, which makes the topics less unique and your results will be less helpful. And so we have several mechanisms to fix these things. For the semantically insignificant words, the user can give a blacklist, which is basically a list of words that the user knows they want to be removed. So there are default lists of English and Latin stop words, depending on obviously which corpus you're putting in. You can add which have the, and many other standard stop words. For the overly frequent words, we offer an upper limit. Basically, it's a percentage that the user puts in where any word that occurs in greater than that percentage of documents in the corpus, those will be removed. Similarly, for the infrequent words, we have a lower limit. It's the same idea. The user puts in a percentage. Any words that occur in fewer than that percentage of documents will be removed as well. And for names, you can use the blacklist, or if they're a main character, they're mentioned very often, you can also rely on the upper limit to catch them. We also have document chunking. The best case scenario for document chunking is using a CSV where the chunks are already laid out, or using a split string. And so that means that you are splitting up the document based on chapters, books, something like that, something the author has written into the text. And so you get these irregularly sized documents, but that's actually a good thing, because we're running LDA with this assumption that each document in the corpus has its own signature distribution of topics. And it's more likely that if we do that based on how the author separated it, then that will be the case. You can see that if we're using a different method, by the length of the document, we have regularly sized documents, but we might be cutting in the middle of a sentence, and you're just less likely to get unique topic distributions for your documents. And we also have the hyperparameters. Those are the sort of probability smoothing parameters that Estelle talked about before. So the main thing you just need to remember about those is that they allow, alpha allows documents to take on new topics, and beta allows topics to take on new words. And so once LDA is done running, it dumps all of its data into a JSON file, which will later be read by our UI. And that contains these familiar data structures that Estelle talked about. And so yeah, the next step is figuring out how to visualize it.
So we spent a lot of time working on our LDA algorithm. We put a lot of thought into it, but it didn't take up all of our time, and we still had one problem to solve. As Brendan just mentioned, the output of our algorithm is this long JSON file of all of our data, which is line after line of word after word and number after number, and it starts to feel dizzying. So this is not user-friendly. I love enormous files of data as much as the next person, but it is hard to get any useful information out of this. So we decided to build a tool, because the purpose of this project was to be able to pull substantive observations out of our results. So we built a user interface that allows the user to explore different results in the context of the text. We have, before we go into detail about what those visualizations were, we have a quick demo video that will take you through an example. And since I'm assuming most of you don't actually speak Latin, we're going to use an English example, although it does work on Latin. That's the point of the presentation, or of the project. And the example that we're going to be using is the story of King Arthur. So this is our sparse but powerful home menu. A lot there. And one of the eventual goals of the project, which we haven't gotten to yet, is to integrate the algorithm with the UI. As the project currently stands, you have to run the algorithm separately and then take the results file from that and put it into the UI. But the algorithm takes a very specific configuration file format. We wanted to make it easy for the user to create that. So we created a form. By clicking Create Config File, it will take you to that form in a moment, which has all of the parameters that we've just talked about, like the number of iterations and the number of topics. I won't go through an example right now, that would take a while, but once you're happy with your parameters, you can click Create Config File again, and it'll download a file to your machine. You can then run LDA from the command line using that file that you've just downloaded, like so. Now that's going to take 2 hours to run.
So we'll skip ahead. Once you've got an output file that you're happy with, you can head back to the main menu and click Upload JSON file and upload the file that was just downloaded from the LDA algorithm. Once that file has finished uploading, you'll be taken to the main visualization screen. On the left, you'll see 4 tabs, one for each visualization tool. Easy navigation between those tabs. The first tab you're taken to is the metadata tab, which has some information and some buttons that we'll talk about in a few minutes. But the main feature is you're able to scroll through all of those topics, all of the words in any topic, which is useful but a lot of information. So if you want to be able to look at a topic in a more visually appealing way, you can head to the word cloud, which has each topic beautifully rendered. Once you've picked a topic that you're interested in, the heat map tab allows you to look at the topic, the distribution of the topic across the full text. You got a sneak peek of that earlier. Finally, if you want to look at the topic in the context of the full text, the annotated text tab has a full recreation of the text, your original input file, and has some fancy highlighting that we will also talk about in a few minutes. And that is our user interface. So as you can see, there are a lot of different visualizations that work together so that you can look at topics in multiple contexts and at multiple scales. Before we talk about those in detail, a quick note about the languages that we chose. We wrote our code in HTML, JavaScript, and CSS, and we used also the D3 libraries. And this runs on the Electron platform, which is basically a platform that allows you to run code written in the web languages on just as a desktop application, so you don't need the internet. So, back to the metadata tab. The metadata tab is the first thing that the user sees, so it's got some basic information in case you forget what your model, like how many iterations you have or how many topics you used. It also includes stop words, so we've talked about that a little bit earlier. The algorithm generates stop words, and you can also put in stop words if there's something funky going on, there aren't words included that you expect there to be, you can check those out. Of course, it's got the full list of each topic, so you can explore that. And if there's a topic that you're particularly interested in and want to keep track of that because maybe it's a topic all about kings, then you can nickname it the king topic. Word cloud.
All right, so what if now we're already familiar with the given corpus? One of the first things we generally want to see in our output is the topics themselves. We want to know the words in our topic, understand which ones are the most important, and notice any interesting or unexpected inclusions in the topics. This knowledge can improve our understanding of the corpus. While our metadata tab has a comprehensive list of every word in each topic, it's not great for quick understanding or attention-grabbing data. We wanted a quick way to view the words in a topic, have a sense of how often they occur, and notice any unexpected or interesting co-occurrences of words inside the topic. For this data visualization, the word cloud performs the job admirably. Borrowing code from Jason Davies, we automatically construct word clouds of varying size for each topic. By taking into account the incidence weights associated with words, it's able to showcase their relative importance. So this is a real-life example from a topic of a word cloud, of a topic generated from the death of Arthur. So since people are naturally drawn to large words and things in the center of the screen, the generation algorithm correlates word size with frequency and places the most important words near the center. In order to make them easy to see and distinguish them from each other, we give important words a unique color too. So what is this topic? We have the words shield, we have road, smoke, horse, joust. It looks like we have a jousting topic. When we look more closely at the words in the background, we can also see that jousting is not taken lightly in this text. We can also find the words tournament, enemies, savage, and revenge. It's these words of contention that add some nuance to our topic. Indeed, the book has some pretty heated jousting matches, and we can glean that almost immediately just by viewing this word cloud. Here's another word cloud that succinctly depicts a common theme in the death of Arthur. Death. Here we have slain, death, destroyed, revenge, slew, sorrow, pity, and my personal favorite, alas. The strong association with the word brother sure is interesting, but I'll let the English majors unpack that one. By now I've confirmed that the text has a few coherent and distinct topics in it, and I may have nicknamed several of them using the metadata tool. My next questions may be, what role do these topics actually play in the text? Are they prevalent throughout or confined to one section? Which of them occur near each other? It's in answering these questions that the word cloud is less useful. Fortunately, we have other data visualizations that address these very problems.
Right. So once you understand the topics by looking at the word cloud, you can move on and take that understanding and apply it to the entire text using the heat map. So the heat map shows the prevalence of topics strewn throughout the text based on location. So this can tell you some really interesting things about topics. For example, whether or not it shows up in a few discrete locations, whether or not it's scattered throughout the text, or if it's concentrated heavily in just one area. So another feature that we have on our heat maps is smoothing. So smoothing takes the prevalence on a single slice of the heat map and blurs it outwards a bit, adding it together where there's overlap. So users can choose the level of detail that they want using smoothing, ranging anywhere from a very fine, laser precision level of granularity down to more of an at-a-glance summary, or anywhere in between. But the heat map can't tell you what's happening in the text at any specific point. For that, we need another visualization.
So finally, if you want to get an idea of what your topic looks like in the context of the text, you can head to the annotated text tab. So the main feature of the annotated text is, of course, the text itself. If the user originally loaded in a text file that included punctuation and capitalization, that all gets reloaded back into this. But if the user originally uploaded a CSV file that just had the words with no punctuation, obviously we can't make up punctuation, but you can still figure it out. We have page navigation at the bottom, so you can easily jump around in the text. We have topic highlighting on hover. So as you hover over any word, it will highlight in yellow all of the words in that topic. It can give you a quick idea of what might be more interesting to look at in more depth. And then if you find something you want to look at in more depth, you can use the static topic highlighting on select. So at the top, we've got those 3 selector boxes that allow you to compare up to 3 topics at once. We also integrated the heat map with the annotated text. So on the right there, you'll see what looks like a vertical heat map, which is actually a heat map of topic 1. You can pick any topic to be the heat map scroll bar, and that allows you to scroll through the text. And we also integrated the two so that you can jump back and forth really easily. We've got another quick video. So let's say that you are looking at the heat map, and you want to check out a section of the text that interests you. And scroll through and pick maybe a really dense section. By clicking on the heat map at that location, it'll take you to the annotated text at that location. Likewise, if you're scrolling through the annotated text and want to see how a specific word fits into a topic distribution as a whole, or how the topic at the location fits into the entire text, you can click on that word and it'll take you back to the heat map for that topic. And that is our entire user interface.
So now that we have both an algorithm and a way of viewing its output, what have we learned about the bead text? So we ran the bead model a bunch of times, and one of the topics that kept coming up was this one. It contains the names of different peoples, like the Picts and the Scots. So when Austin was looking at the data, he nicknamed it Peoples of Britain. This topic is one that someone studying Bede would probably expect to see. At the beginning of the text, Bede describes the island and its inhabitants in great detail, and you can see that this topic clusters at the beginning of the text. The topic doesn't just mirror that chapter, however, since if you click through in one of the slightly green areas, more toward the middle of the excerpts, the topic is still pulling in the names of peoples like the Scots and the Picts. Another topic that kept coming up was this one, and it's not something a Bede scholar would necessarily expect. Remember that Austin wondered whether a secular powers topic and a church topic would show up? This one's a little of both. It contains rex, or king, and episcopus, or bishop. It seems a little hard to nickname for now, so let's find out more. On the annotated text tab, it seems like kings and bishops are actually in scenes together, as you would expect from this topic. But see all those NA markings? That means that those words in the spreadsheet haven't been limmatized yet. The bead addition work is still ongoing. So this topic isn't a fluke, since it showed up many times in our models. But there's a good chance that if we had those limmatized words, it wouldn't actually be showing up. That's one of the limitations of our tool.
Right, and as Bart said, while topic modeling is a really powerful tool for giving new and interesting insights into the text, it can't actually interpret the topics for you, so that leaves a lot of room for human error. So people come to the text with existing biases, and it's easy to imagine that two people might draw very different conclusions based on the fact that God and worship are in the same topic as battle and treason. So another drawback of LDA is that while ideally LDA identifies themes that exist in the text, and is usually very good at doing so, it can also pick up other frequently co-occurring clusters of words. So for example, this topic seems to be more of a reaction to a generally increased level of formality at the end of the story of King Arthur, especially related to swearing oaths. So another place where LDA can go wrong is based on the number of topics that you have. So let's say that you have a bunch of themes in the text, which will say that themes are distinct clusters of related words that we're displaying as colored circles. And you've also got a bunch of boxes, so those are our topics in LDA. So LDA will always put all of the words in the text into a box. But what happens when you have too many boxes relative to the themes that you have in your text? Bad stuff, as it turns out. So what you can see here is that sometimes a theme can get split up into two different topics, creating a kind of false dichotomy where it appears that there might be a difference between the two topics when really you just have too many. Another bad thing that can happen is you can just have a topic that's filled with nonsense words or leftovers basically shaved off from the other topics. And of course, if you have too few topics, then bad things can also happen. So you might just lose a topic entirely, and you can also end up with Franken topics. So topics that are made up of two or more themes, which can be very confusing, and if you don't have a really good tool like the heat map and annotated text to go and understand what the topic is, could potentially fool you into thinking that these themes are related when they might not actually be. So those are some of the things that are holding us back. But we also have some things that we can do going forwards. So one thing that we might do if we had more time is add more Latin-specific optimization for text files. We had originally thought that our use case would only be importing CSV files, like the format that bead is stored in. But we expanded that at some point to include text files as well. But Latin text files don't really work too well in our model. So we could account for some of the eccentricities of Latin, such as the overlap between V and U in running LDA. We could also programmatically determine the number of topics to mitigate some of the problems that I just mentioned, and also automatically limitize words. Keeping in mind that the last 2 points would be truly monumental tasks, possibly worthy of comps next year. So one thing that is missing from our visualization tool, just because we didn't have enough time to add something like this, is a way to really explore the topics based on the words based on the topics that it is a part of. So, for example, if you were interested in really examining the word magic, you might be able to see what proportion of topics it inhabits. So finally, a few miscellaneous things that we could add. Chunking, as we've mentioned, is a very important part of LDA, but it isn't really displayed at all in our visualization tool. So we could add indicators of chunking to our heat map and annotated text, And we might see interesting patterns, like a topic occurring at the very beginning and very end of a chunk, that could tell us more about the text. So another thing is, because this is topic modeling of Latin text, translations for Latin. Granted, I don't know how many people that can't read Latin will actually be running Latin text through our tool. But as someone that can't read Latin and has run a lot of Latin text through this tool, this feature would be appreciated. So that is our comps. Thanks very much for listening, and a big thank you goes out to our advisor, Eric Alexander, and Austin Mason for being such a great resource as well.
You guys mentioned that it takes a long time to run, and that's partly, just unavoidable. But did you try to speed it up anywhere with like PyPy or something like that?
Okay, so the question is, did we try to speed it up?
So the data structures we chose to do, be able to update things by index, that was already speeding it up a lot. Python in itself, maybe not the best place to start if you're trying to make things run fast, but we chose the language because of the users we were expecting to have. And we did not do much research into libraries that we might be able to use to speed it up.
Part of that is also the nature of the beast. You're running for every topic, for every word in the corpus, you're running through every topic just to make one topic assignment. And then you do that thousands of times. If you have 500,000 words in a text, it's just going to take a while.
So on your smoothing slide, I noticed that you had the drop-down menu for selecting a number. Could you elaborate on what exactly that number represents when it comes to the whole class?
Sure. So this is asking about, we had a drop-down related to smoothing. So it's a bit esoteric, but that's actually the number of pixels outward that you blur the prevalence. So if you imagine the prevalence of area that you're actually smoothing outwards as kind of a straight line, that would basically make the center point of a triangle that goes out to either side of decreasing, basically adding a decreasing amount of prevalence to all of the areas around it.
Is there some version of the LDA algorithm that could look for longer phrases instead of single words?
So during our lit review, we found an article about using n-grams to learn not just about words that are related because they're in the same document, but words that might be even more closely related because they show up sequentially together, like latent Dirichlet allocation. You can think of it as one concept, and so those three words would be showing up in that sequence often, and using n-grams would be able to find that. But we didn't use that because Latin word order is not like English word order. And because of this inflection system that I talked about earlier, word order can basically be whatever you want it to be. And words that go together because of their inflected ending, the reader can still figure out that they're related. But n-grams wouldn't be helpful with that.
Do you know the history of why Dirichlet's name was on this method?
I don't know. Yeah, the question was about why Dirichlet or Dirichlet's name is on this algorithm. So I personally don't know too much about how the statistics of it all works, but this algorithm is sort of a general form of PLSA, which is one of the earlier algorithms from 1999, which is probabilistic latent semantic analysis. And that is sort of a more specific form of LDA, and so using Dirichlet priors, PLSA was generalized into LDA, and so if we specified the Dirichlet priors in a specific way, we would be able to run LDA exactly like it was PLSA. Yeah.
Can you talk about the practical research applications of what this modeling technique might mean?
So we did, I can imagine using this as a researcher later, as a humanist. I don't think the kinds of testing we were running were necessarily bringing up the kinds of questions I would want to bring up if I were using this as a finished tool in real life. But some things I've read about topic modeling being able to do is, for instance, in languages that we don't necessarily know super well because we have very few, comparatively few extant corpora. For instance, Anglo-Saxon English. Topic modeling has shown that two words maybe that we knew, one of them that we knew, oh, it means some kind of fortification. And another word that we know, oh, it means some kind of leader or ruler. Topic modeling let us know that those words were semantically related. That this ruler owns this kind of fortification, which we wouldn't already otherwise have known. Topic modeling can also just sort of sort journal articles. That's one of the ways it's being used. Is, you put all the articles through topic modeling, and then you can search by a topic you might want. That's less discovering questions that you wouldn't have thought to ask, and more sorting. But it has a wide range of applications.
I would add that you can also apply it to computational biology and image processing, and there's a lot of research being done right now that's trying to run, as I briefly mentioned, like running LDA and other topic modeling algorithms on really big, like masses of social media posts, like tweets, and like finding ways to put them in together into coherent documents, and try to find patterns in like really large information sets that like could be so all over the map.
Given that the selection of the number of topics is a parameter in the algorithm, is there something in common about having to run the algorithm iteratively to find the right number of topics, or is this something that people just pick a number and hope that it produces something productive?
Yeah, that's something that we struggled with a lot. For us, it was mostly just testing, seeing what specifically worked for different lengths of documents. It definitely depends on the length of documents and how similar the documents are.
There are a number of metrics you can use to measure it. We didn't build this into our algorithm, but one thing you could do is have a metric, something that basically tests how similar topics are, something that can find whether or not there are two topics that are too similar, and then reduce the number of topics, run on it for another iteration. So that's another possible extension.
So knowing that your code might take up to 2 hours to run, and that no code is ever perfect on the first run, what were some of the ways that you went about debugging your code other than waiting 2 hours for it to run, just to see if there was a bug?
So as far as the algorithm went, we tried to start and have as few bugs as possible by drawing out everything we were going to need and being really specific about the sort of modules that were going to work together. When we were debugging it, we made a corpus that was 10 words long with 3 and 4 word documents, and asked it to find 2 topics. And this was small enough, we called it Tiny Test. This was small enough that it didn't actually take too long to run, and we could easily find the bugs. As far as debugging the UI, we ran some extremely deprecated models. For instance, we would run 1 iteration on a model. And so when you load that into the visualization, it's pretty funny. You see the heat map tab. It's just blocks of color because there's no clustering at all. But it's good enough for the debugging.
Yeah, like, on really, really long text, like if we ran on the Bible, that would take a few hours, but like a lot of, because of like the size of feed, like not actually being all that long, we would usually run it on like smaller scale text, and like, depending on the number of iterations, it would take normally 5 to 30 minutes on most of our things we were interested in.